All right. Hey, how's it going? So this is Ashton, and I'm here to show my FSM for the in-class assignment for March 29th. So here you see my VHDL file. This is just my implementation of my FSM. So here's my entity. I'm taking in a clock, a reset signal, and the change state signal as specified in the in-class assignment, and I'm outputting whatever my current one-hot encoding state is. So in my architecture, because this FSM is really small, it's probably not going to use one-hot encoding natively to implement this FSM, so I'm going to manually give it a one-hot encoding. So I do that by making my state a standard logic vector, a bit vector that I will control manually. In my FSM process, I have an active low reset that resets the state to state 1. And then if reset is 1, so we're not resetting, we are ready to do normal operation, then just on each rising clock edge, it's going to look at state. If I'm in state 1 and change state 1 is equal to 1, then move to state 2. If I'm in state 2 and change state is equal to 1, move to state 3. If I'm in state 3 and change state is equal to 1, move back to 1. And then if there is any sort of glitch in my state signal, then I want it to just go to 1 immediately. So that's my entire FSM. Nothing crazy, pretty simple. In my test bench, I have just included my components in the architecture of my test bench. I've decided I'm going to have a clock of 10 nanoseconds, or with a period of 10 nanoseconds. That's roughly 100 megahertz. I've got my input signals here, my output signals. There you can see I'm just I'm instantiating my component. Here is my clock creation process. And here in my stem process. So what I'm going to do is I'm going to test my reset functionality. Just going to set it active low for 3 clock cycles while change state is active to see does it keep the state at 1. Then after I activate the device, I'm going to set reset high. I'm going to see does it flip through the states as it should. And I'm going to turn change state low and see what happens. So I've already got my waveform pane open, but as you can see it's at 0 nanoseconds. I'm going to run it for 200. We're going to pop out my waveform here so it fills up my screen and zoom to fit. So, okay, here we are. I'm not showing my clock. I'm really just showing my reset and my change state. And as you can see from here, when reset is low, I actually do need to show my clock here. Okay, let me see if I can add my clock to this waveform pane. Not sure why that got deleted. So let's put that up there. We'll restart. Sorry for this problem here. All right, now run it for 200 nanoseconds. There we go. Now we've got a true clock. Let's pop it back out. It's maximized. Now let's zoom fit. Okay, now you can see the clock. Sorry about that. So, as we can see, while reset is low, the device should just stay in whatever the default state is, which was state 1. Once reset goes high, this device is enabled. It's at that point, once it's enabled, on the next clock edge is when it will start executing as normal. And we can see that here. So reset enables right here, and clock goes high right here, but it's not going to change state here. It's going to give it a clock cycle, and then normal operation will continue. And we see that's what happens here. On the next clock cycle, we go to 2. On the next, we go to 3, back to 1, 2, 3. We hit 3 here, and then I say don't change state anymore. So it just stays in this change state until I re-enable state changing, and then it resumes as normal. So here we go. Proof that this design does actually work. What's happening here with this reset going low is it's just repeating my test bench. It's going to keep cycling through my test bench forever. So yeah, here we go. We've got proof of functionality of this FSM from March 29th, 2021 in the Embedded Systems class here at University of Memphis. You have a good day.